Good afternoon and welcome to this edition of the CMCC webinar organized in collaboration with Climate and EUCP Horizon 2020 project. My name is Jaroslav Mysiak and I'll be moderating this webinar. Our guests today are Francisco Doblas-Reyes, who is the director of the Earth Science Department at Barcelona Supercomputing Center, and Jason Lowe, the head of climate services at the Met Office Hartley Center and the coordinator of the EUCP project. CMCC Euromediterranean Center on Climate Change is an Italian research institution that is looking at all disciplines that are somehow contributing to the climate science, and the analysis of the climate change impacts. So the mission of CMCC is to investigate and model our climate system and in the interaction with society so as to provide a reliable, rigorous and timely scientific result to stimulate sustainable growth and protect the environment. We are organized along 9 research divisions, starting from advanced scientific computing, climate simulation and prediction, economic analysis of climate impacts, risk assessment and adaptation strategies, ocean modeling and prediction, and regional models of hydrological impact, as well as sustainable earth modeling economics. Our offices are all over Italy, and you are well welcome to come and work with us in Italy on the global issues related to climate change. This webinar is organized in collaboration with Climate Europe, which is a coordination and support action on bringing together all projects on climate services and facilitating the coordination and exchange across the Horizon 2020 projects. And the second project that will be featured during this webinar is EUCP, but that project will be introduced by Jason. Just one practical issue. We will listen to 2 talks by Jason introducing the EUCP project, and then by Francisco talking about the specific climate projections being developed by the project. After the 2 talks or during the webinar, you might post your questions. There is a tab on your panel, webinar panel, which is called questions. So feel free to post the question whenever you like to. And if I may ask, just introduce your name or the context why you are asking this question or what might be the implication. Thank you very much. Jason, may I ask you to take the floor and introduce the EUCP project?
Okay, thank you very much for the introduction. Hopefully my slides will be appearing now. Here they come. Thank you very much. So EUCP is an H2020 project. It started about 18 months ago now, and the name comes from EU climate predictions. The aim of the project is to provide research on a climate prediction and projection system for Europe, going from roughly a season ahead out to 40 or more years into the future. And the scale of the project is around 13 million euros. And you can see at the bottom of the slide, we have quite a large number of partners bringing a whole range of different disciplines into the project. If we look over the last 12 months, it's actually been an incredibly busy year for several nations producing their own national climate projections. So in the UK, I personally was heavily involved in the production of UKCP18, where we produced a range of topics and a range of tools. We co-developed those with users. You can see it in the upper diagram here. The headline result for the UK was a greater chance of warmer, wetter winters and hotter, drier summers. But this is going on across Europe as well. So in Switzerland, a new set of national scenarios were also launched, also in November last year, but using very different techniques, using regional climate models and drawing heavily on existing results from projects like Eurocordex. The Dutch are currently working on their next set of climate scenarios. But what if you want to look at the next generation of scenarios? That research needs to take place. What if you want climate predictions and projections for nations that don't have their own scenarios? And what if you're interested in impacts that cross national boundaries? And this is where I think EUCP can help. So within EUCP, we're addressing a number of research questions. The first question is looking across timescales. So the upper part of this diagram, you can see we start thinking daily weather forecasts, seasonal forecasts, decadal predictions, and multi-decadal climate change projections. There are systems that exist on all of those timescales. But what if you want to look seamlessly across those timescales? Well, there's a particular issue thinking about this period of roughly 1 to 10 years, where we have information from the initialized predictions and the longer-term climate projections. And EUCP will carry out research to really understand that period where we have the overlap, to understand the skill and the advantages and disadvantages of comparing the initialized forecasts with the long-term climate projections, and ultimately help users use the best set of information from both of those types of tool. Now at the bottom, I've put a few pictures from the farming sector. And I did this because I had the pleasure last week of going to a workshop where we had farmers from the UK, but we also had seed merchants, farming consultants. We had people considering long-term infrastructure funding within farming. And when we start to look at those decisions, it becomes really obvious why we need to think across the timescales. With at the shorter end, decisions on planting and harvesting dates. Moving into the seasonal, we think more about seed choices. But as we go further in time, we might want to think about development of new seed varieties. As we get to the longer timescales, then we start to think much more about infrastructure developments on the farm and potential diversification of the farming business. And in fact, one farmer really put it very succinctly: by the time you're getting to 30 or 40 years, really, you're talking about whether the farm will exist for the next generation and how you do that. So this view across timescales is essential. The second big question for EUCP is how can we make more and better use from collections of model simulations? And I'm showing in the upper figure the sort of diagram you will have seen in reports, for instance, from the Intergovernmental Panel on Climate Change, each one representing a different model or a different simulation. And that's great, but there's more information there. And typically at the moment, each model gets equal weighting, one model, one vote. In EUCP, what we want to do is really move forward the idea of, well, perhaps some models deserve more attention, perhaps some models deserve a greater weight. And we can use, for instance, the agreement of the models with the observations to help us understand how to select those appropriate models. And EUCP will carry out research across a number of different methods for doing that, because it's likely there's no one method fits all. The method chosen needs to be appropriate to the question. And the reason for doing this is quite simply, it will enable better long-term planning and adaptation decisions to be made, whether we're looking at something like a coastal barrier or whether we're looking at urban developments like green roofs shown on the right-hand side. The third element of EUCP is about trying to better simulate extremes of weather and climate. We know many impacts are associated with weather and climate extremes, but when we look in the current generation of climate models, often they're not able to simulate the most extreme events. And if we look in the regional models we've traditionally used, they're now getting down to scales of the order of 12 kilometers. So they can better represent coastlines, they can better represent mountains, but they're still not able to represent or explicitly permit convective activity within the model. That's represented much more simply. So now there is a new generation of regional models called convective permitting models that are just emerging and starting to be used. And we wanted to bring them together and cover all of Europe. And you can see how we're doing that in the left-hand plot. So each of those regions has at least 2 models of this new convective permitting type with scales of less than 5 kilometer. We also have a region over the Alps, and you can see a plot on the right-hand side where all models taking part produce results. And here the aim is to understand how the different models compare and baseline them against each other. And the purpose of this is to enable this better simulation of weather and climate. So when we take all those 3 components, the seamlessness over time, the improved use of ensembles and higher resolution, EUCP then takes those into the user domain. So we have a wide range of users who take part in multi-user forums, and we're adding to those at the moment. We also have a smaller number of users where we have deep dives and actively work with those users on aspects such as coastal flooding and erosion, urban flooding, renewables in the nearer term, to understand how we can better use the science. I think that's probably a good place to stop the introduction.
Thank you very much, Jason. So shall we continue with Francisco's presentation on the climate prediction systems being developed on the EUCP project? Francisco, the floor is yours.
Thanks a lot, Jaro. Let me thank CMCC and also EUCP for organizing this webinar, and also Climate Europe for also promoting it and coordinating with EUCP and CMCC to basically make it more useful for a larger community. I'm Francisco Doblas-Reyes, and I work at the Barcelona Supercomputing Center. Let me make this smaller, and my screen wasn't being shown. Okay. So I direct here in Barcelona the Earth Sciences Department, and I work mainly on prediction timescales, and this links very nicely to some of the things that Jason has introduced in the previous minutes. This is a modified version of one of these slides that Jason has shown, in which I try to illustrate what are the timescales for which decadal prediction is really playing a role. These are the timescales covered or encompassed by the rectangle, the red rectangle that appears there, which has on one side to the left the weather forecasts, which are mainly initial value driven forecasts or simulations, while on the right it leaves the climate change projections that are mainly driven by boundary conditions, so basically the changes in the atmosphere composition. And this means that the climate predictions, which covers seasonal, and decadal forecasts, and that go for timescales that range between a few weeks into the future up to 30 years, are basically problem that is both driven by the initial conditions and also by the changes in the atmosphere composition, which makes that it has to make the most of the fields of weather forecasting and also climate change projections. The interesting aspect of climate predictions is that they focus on timescales for which there are users that have to make decisions in the near future, in what is known in the field as near term. The other aspect that is specific of climate predictions and that is shared also with weather forecasting is that the simulations, the predictions are compared over the observational periods with the best observational data sets available. But instead of looking at the model climate or the ability to reproduce the observed climate with a model, the intention is to also try to simulate and predict into the future the observed anomalies at the time when they happened. And this is very, very specific and very demanding as well as a task. But within the context of EUCP, as Jason has introduced, one of the main challenges is to provide climate information, not just climate data, but climate information as far as possible into the future, going well into the climate projection timescale. In the case of EUCP, it goes as far as 2050 for a set of identified users. And this difference between climate data and climate information is key for this presentation. In the past, the climate community, the climate research community has worked with an idea in mind in which we saw ourselves as data producers that would eventually be used by a range of users that will be running some impact models. These we know now, and we acknowledge that this is a very an oversimplified view of the problem. And most of the community is moving to a slightly different way of working in which we use a service-oriented research agenda. And this is very different from what we were doing before, in the sense that we are not just producers that deliver data, but we are part of a chain in which climate scientists develop models and observational data sets that are tailored for the uses that are identified by a number of stakeholders, and they feed a service that is developed using user interface platforms and mechanisms so that they allow decision making to happen to address risk management, adaptation, and policy making. And at the same time, these arrows go in the other direction, in which the users, the stakeholders, decide what they want from that service and in which way. They identify also problems that are relevant to them that usually data providers haven't really thought about. And this information is fed back to the observational scientists and the model developers so that they can focus on processes, variables, and problems that were not considered before. And for this change to work, it requires a different way of addressing research in the sense that it's basically transdisciplinary research in which social scientists, economists, software engineers, communicators, and climate scientists work together and communicate and have platforms in which the information flows from one side to the other, without really saying which one is the most important. In any case, this service-oriented research agenda doesn't preclude the fact that basic research is at the core of progress and innovation. But this basic research shouldn't be understood just as a way of improving our models, which require a continuous model development, but is basic research in all the aspects of this chain. Let me go to the definition of what we understand by focus products and how we assess their quality. And quality is an important aspect from an operational point of view because it's an aspect that is basic. It's part of the basic communication with the users and stakeholders. So somehow a forecast itself doesn't have any value and any usability if it doesn't come with an estimate of its quality. So the definition of the product is very important. So thinking of the focus as just the simulation coming out of any of the focus systems that are out there, for instance, to the climate change, the Copernicus Climate Change Service, there are 5 seasonal focus systems contributing: ECMWF, Met-France, Met-Office, DWT, and CMCC. And we cannot just simplify the problem of the issuing of products and their quality to assigning a quality to each one of these different focus systems. In the sense that each one of them, as I'll show next, has strong and weak points that have to be identified depending on the product, which should be issued on the basis of what the users are actually requiring. The verification metrics used to assess the quality is actually something that depends also on the observational reference used. The quality has to also be compared to a standard that could be a naive forecast, or it could be a previous focus system in case we're interested in the evolution of the quality of the focus products issued by different focus systems or different versions of the same focus system. And we need to define also what is a focus product with high quality. So we need objective criteria to define when we are improving over a reference prediction. The focus quality, and I'll emphasize this again, is only valid for a specific focus product. So if we are talking of precipitation over Europe in summer produced with a specific way of combining the ensemble information from a focus system, the focus quality will be only valid for that product and not for anything else, not for temperature or for any other season of the year. And in any way, in any case, there is the aspect, a key aspect when communicating to the users, which is the value of a product. So the value is very different to the quality, and it's a property of a focus product that can only be defined by the user itself, because it's only the user who knows what the impact of a specific decision might have in its own decision chain. This is an example of a focus product, very simple example in which you can see a PDF for forecasts of wind speed over North America for the late winter of 2015. So the average is over January, February, March. And each one of the PDFs that appear there are different in the sense that they are issued for January, February, March with 1 month on the right, 2 months in the center, and 3 months lead time. So the leftmost PDF has been issued with a 3-month lead time, and it was formulated at the beginning of October. So we have different focus products for the same focus targets. So if our target is January, February, March, we can issue that forecast with different lead times. And this is not different to what is being done in weather forecasting. And the same applies to other climate forecasts for subseasonal forecasting or for decadal predictions. So for instance, in decadal prediction, every year, the focus prediction centers make a forecast for the next 10 years, and those forecasts overlap for the future. And this is, again, an important difference between climate forecasting and climate change projections. The other thing is that you can see on the bottom right table illustrating several measures of the quality of these forecasts. So the wind speed forecasts for January, February, March 2015 with different lead times and different measures of these forecast quality, correlation, and several measures of the quality of the probabilistic forecasts. However, while there is uncertainty in the forecasts themselves, and here the uncertainty is illustrated in the form of probability density functions, there is also uncertainty in the forecast quality measures. And this is a very important aspect to be communicated to the user. So we have to communicate to the user the forecast, its uncertainty, the focus quality, and also the uncertainty of the focus quality. How large is the uncertainty of a focus quality measure? Here you can see an illustration again for seasonal forecasting, for prediction of the ENSO, the linear southern oscillation, as a function of the focus time in the horizontal, going from May to the month of August. So these are forecasts for 4 months into the future, and we can see that there are ranges around the correlation of the ensemble mean of the forecasts issued with the ECERT seasonal forecast system. And those ranges illustrate the different sources of focus quality uncertainty that play a role. In green, in purple, you can see the role that plays in the uncertainty, in the focus quality uncertainty, by the limited rect length that is being used to estimate the focus quality. In this particular case, it was around 20 years that were used to estimate the correlation between the observations and the predictions. In orange, you can see the contribution to the focus quality uncertainty coming from the limited ensemble size that we are using, which is a relatively minor contribution to the uncertainty, in particular in areas where the scale is high, like in the tropical Pacific for seasonal timescales. And in green, we have a very interesting source of uncertainty that is affecting many different aspects of the production of climate information, which is the observational uncertainty. When we are estimating the focus quality, as I said before, we are comparing to an observational reference, but that observational reference also has uncertainty itself. So the green area there is an estimate of how the observational uncertainty is contributing to the focus quality uncertainty. And we can also see it, this as the impact that that verifying our forecasts against different observational data sets might have. So if we verify the same focus that I was referring to before, so ECERT seasonal forecasts over the period 93 to 2009, over the tropical Pacific for SSTs, ensemble mean. In red, we have the verification against the ESA CCI SSTs, and we see that they are very different in terms of the correlation when we compare it to the verification of exactly the same seasonal forecasts. So we haven't changed our simulations, but verified against the ERA-Interim SSTs, ER SSTs, or HAD SST datasets. So these are very substantial differences in our estimates of the quality of a forecast that has to be communicated to a user. There are other aspects of research that are fundamental to operations, in particular when it refers to the interaction with the users and the identification of the products that we can provide them. We know that our models have systematic errors, and the results have to be bias adjusted. And there are many different methods for bias adjustment, and I'll mention some of them next. And another aspect that has also been mentioned by Jason is how to combine different focus systems or different climate sources of climate projections. And there is no analytical solution for this. So we need to really find a pragmatic way to make use of the different options that we have there and communicate all this in a proper way to the users. This is an illustration of the impact of the bias adjustments, and you have in the columns 6 different bias adjustment methods used in seasonal forecasting context. The same results that I'm illustrating here are valid for subseasonal and decadal prediction. And these are results for the temperature forecasts over the Southeast Asia and tropical and the maritime continents from the ECMWF system for forecast system verified against ERA interim for the boreal summer temperature. And what we can see here is that areas in red are those areas in which the skill of the system is degraded in certain aspects because of the bias adjustment. And areas in blue are those areas in which the bias adjustment bring some improvements in using this focus quality measure here, that is the ranked probability score. The three rows that appear there are different flavors of the focus system. So the focus system using short verification periods, 1994-2014, in a small ensemble. The central row is by increasing the ensemble size to 51 members. And the bottom row is for the focus system considering the whole verification period, 1982 to 2014, and 51 members. And what we can see is that there are some areas that appear in blue. These are areas in which the bias adjustment methods are correcting for some aspects of the systematic error that are important and I would say fundamental to the users, which is the lack of reliability. So the four bias adjustment methods that appear on the right columns are those that can correct for the lack of reliability. But there are still many areas in which we have a degradation of the skill by using bias adjustments. And this degradation of the skill is unavoidable. It's something that is due to the fact that in any bias adjustment method that we use, there is an estimation of some parameters. Even in non-parametric methods, we have estimations that are necessary to compare the observations and the simulations, and that degrades the skill in areas in which the basic skill of the system is low. Still, that doesn't mean that the bias-adjusted forecasts don't have skill. They have less skill in certain aspects compared to the raw forecasts from the model, but there is a very important aspect to mention here, which is that the skill of the raw forecasts is low already in areas where there are large systematic errors, and these systematic errors are removed by all these different bias adjustment methods. The other important aspect to take into account when we are talking about bias adjustment is observational uncertainty. So I mentioned the role of observational uncertainty when we are making focus quality assessments, but observational uncertainty also affects bias adjustment in the sense that when we are bias adjusting, we usually consider only one observational reference. What happens if we consider more observational references, and is that really needed? In seasonal forecasting, what we are trying to do is to bias adjust mainly the interannual variability of the variable that we have an interest in. So in the left column, we have results for 10-meter wind speed, and in the right column for 2-meter temperature. And what you see there is the ratio of the interannual standard deviation of the ECMWF system for focus system, and ERA trim at the top, GRA 55 at the center, and MERA2 at the bottom. And we use reanalysis for this comparison because it's the only global data set for instance, 10-meter wind speed. For temperature, we could use something else. But for the sake of illustration, this is already good enough. And what you can see is that the systematic error of this system is different depending on the reference that we use. And we can see this for the 10-meter wind speed over North America and for the temperature over India. So which observational reference should we use when we are bias adjusting? And when we are also taking into account the benefits of bias adjustment. So this is an open question that requires a lot of research, and it's fundamental for the development of climate information and a service. And we also should bear in mind that many users will verify and bias adjust against their own observational preferences, which will also have uncertainty. And it's our responsibility to make them understand that this has an impact as well in the quality of the products that we'll deliver. This is not just valid for climate forecasting, this is affecting as well climate change projections, because there is also some bias corrections that are taking place there. They're slightly different in the sense that they use the observations in a different way. I also mentioned the multimodal as another research approach that is being used to improve the quality of the climate forecasts that are delivered. Again, here you have an illustration coming from seasonal forecasts that we are working to implement as well in a decadal prediction context. The main message here is that there is not a single focus system that is the best one everywhere. And this is what you can see in the top left figure. This is the focus quality measure for 2-meter temperature, probabilistic predictions for boreal winter from 3 different focus systems from the Copernicus Climate Change Service, using the continuous ranked probability skill score metric, which is the CRPSS that appears on the top left of the figure. So the fact that there are different colors appearing in the different areas in the top left figure means that different focus systems are the best ones in different areas for these particular focus products. If we consider them all together and build a multimodel by pooling all the different focus systems without weighting them in any way, we see that we will obtain a multimodal forecast, and we can make also probabilistic predictions using it. We can also consider the possibility of weighting those forecasts, these different systems, by their root mean square error in the past. And if we do this, we obtain the scale that appears in red in green in the top right figure. What we see in the top right figure is the option of the multimodal, whether we use the models with equal weights or with in purple, or with whether we use we build the multimodal by giving different weights to the different focus systems in green. We see that the multimodal, regardless of the option that we take, is giving skill over the basically the same areas that the individual models have skill. The interesting aspect of the multimodal is that it condenses the benefits, the good points of the different focus systems into a single focus. And this is fundamental again for the users, because the users have problems to use information from different focus systems, from different sources. Providing them with a unified source is a good way of addressing some of their requirements. However, the multimodal is not the solution to everything, and we need to consider that the multimodal can only improve if we improve the individual focus systems. And one way to improve them is by increasing the resolution. And this is a very simple illustration, again, using Easy Earth and predictions for the tropical Pacific, in which we can see that going from black through red and blue, the increase in the resolution of the focus systems it really improves the quality of the predictions, in this case in the tropical Pacific. So having models with a high resolution really pays off, and this is an aspect that requires a lot of work from our side. The important thing about increasing the resolution, and we'll have a talk about the impact of resolution on climate simulation next week in this same series of webinars, is that as we increase the resolution, the models need to be computationally more efficient. We are going to require more resources from the machines that we use, and we are going to go through more strict tests for those hours to be granted to us. So this is one of the aspects where bringing in the software engineers in a really transdisciplinary way of performing research is becoming fundamental. One of the reasons why we get better performance in our models by increasing the resolution is that we have more realism in the forecast, in the simulations that we are making. We are introducing eddies in the ocean. We're introducing convection in the atmosphere, as Jason said before. And hopefully this will allow us to bring in those processes that contain predictability. However, this allows me to bring in another very important aspect in climate forecasting that is preventing us from making progress, and that we need to tackle as quickly as possible if we really want to make a change in the climate information that we provide to the users. And this is the model shift, the focus drift and initial shock in those simulations. Most of our simulations start from realistic initial conditions, which means that the model will drift towards its own climate. And as a result, the model will be in a non-stationary state along the forecast time. And this is affecting all climate prediction timescales, from subseasonal all the way to decadal. The problem is that in that context, the models will have a non-stationary climate, and will be affected by how bad the model climate is and the systematic error is. And the quicker the model drifts into its own climate and the largest the systematic error, the less it can take advantage of the of the initial condition information that is provided with initial conditions. In this example, which is I wouldn't get into details, what we looked at is how bad the systematic error is affecting seasonal forecasts of temperature and precipitation over the North American Great Plains in summer. And the reason for this is that the models, and these are results from a multimodel of 5 different forecast systems, the models drift very quickly into a state in which the land-atmosphere coupling is too strong. And the result of this is that the model is not able to make use of the good initial conditions that we are providing for the soil moisture. The only way to address this problem is to look into the processes that are responsible for this bad forecast drift, and to address them in the right way. And the main reason why the models have such a systematic error is the lack of resolution in the atmosphere in that region, the North American Great Plains, that prevent the model from reproducing mesoscale convective systems that are the ones that are recycling the precipitation and allowing the soil moisture to interact with the atmosphere. Unfortunately, that can only be done at very high resolutions, and the interactions with communities like Cortex are the ones that can really make a difference in the way we tackle these kind of problems in climate forecasting. What I've been talking about until now focuses mainly on research and the way research is feeding operations in operational climate forecasting. However, the chain, as I mentioned before, goes well beyond the production of essential climate variables and their post-processing. Actually, the chain that I mentioned until now focuses on the bracket that appears at the bottom center part of the slide here. So to go from raw climate predictions and the assessments of the forecast quality, and it should go well beyond that to create a climate service that can generate and deliver products, and at the same time provide feedback on really what is the value of that product and the limitations for the user. And this is summarized in the staircase that appears at the bottom right, which there are more stairs than the basically the 3 ones that we are basically focusing on traditionally in our community. What are the users of these climate information, the potential users, and what do they want this information for? This is summarized in this very nice diagram by Desai and Marta Bruno Soares, in which we can see that as we consider longer timescales for the climate information, the kind of decisions that the users will make are increasingly strategic. And they go from planning and maintenance activities for their systems, all the way to wider visions and strategy for their organizations. And this is basically covering all the timescales that are relevant for EUCP. And this goes across many different sectors that we have assessed that are mature enough to uptake this type of climate information. Some of the user requirements identified to these dates are summarized here. These conclusions come from analyzing deliverables from a number of projects that appear at the bottom. And basically what the users require are more targeted products that basically are built on climate data, but that look at aspects that surprisingly climate scientists have not really paid attention to these dates. They want to be more involved in user operations and activities. They want to work with the climate scientists and to assess the added value, and to have a proper chain that goes from the product verification and predictability all the way to their own decisions. And something that I mentioned before is that users need the information that is provided to them to be reliable enough, and reliable is a very wide concept in the context of climate information that covers many different aspects of the focus quality and the quality of the model-based information that is provided to them. An important aspect that is also raised by the users is that they are agnostic as far as the distinction between predictions and projections is concerned. And in UCP, there's a substantial effort being made to really find ways to construct single stories that go across the prediction and the projection simulations that we have, so that we provide climate information that is as useful to them as possible across different timescales. I think it's never emphasized enough how important the communication with the users is for climate scientists, and what is the benefit that we can get from engaging more with the users. At the BSc, we work on aspects like gamification, in which we build games that the users can play with, and that illustrates issues to them, like, for instance, the skill of a forecast, and whether they should really pay attention to just the climatology, which is basically what they've been doing up to now, or whether there is something to be gained, and how, from those forecasts. And this is an example that we have built in collaboration with other partners from the EUPORIS and S3S4E projects, in which we try to illustrate to the wind energy sector what are the benefits and where there are potential benefits from seasonal forecasts and in their decision making. Another aspect that the service-oriented research has to address, and that requires the involvement of climate scientists, is the evaluation and quality control of what we provide, be it research data sets or operational forecasts and projections. The BSc is in charge of the evaluation and quality control function of the climate data store of the Copernicus Climate Change Service. And in this context, we are engaging with an increasing number of researchers and practitioners, because we, being in charge of, for instance, the quality control of the CDS data sets, we found out that there are lots of standards that are missing in the data that we are delivering. So somehow there is a lack of professionalization in what we are delivering to the users, and that requires a lot of thinking and a lot of involvement of climate scientists like us. There is a huge effort towards moving what is happening right now in research and efforts like EUCP towards operations, so that they can feed climate service and the provision of climate information. And a good example is what is taking place in the decadal prediction community to provide real-time decadal prediction forecasts. This is right now being hosted and coordinated by the Met Office, and on the right you can see some of the contributors to this effort. Some other efforts are taking place in the context of the Copernicus Climate Change Service, and EUCP is supporting some of these initiatives. There are other more informal moves towards operationalization that are taking place within the community itself, and it's important that climate services are aware of this and feed into these kind of initiatives that are actually very nice and very welcome by a number of stakeholders. And in some cases, the stakeholders are the ones funding these kind of initiatives, such as the one that is listed here as the seasonal hurricane prediction, which is actually funded by a reinsurance company. These are two examples: the CIS prediction network that has been going on already for quite a few years, and the seasonal hurricane prediction website that is hosted here at the BSc, in which operational actors and also the research community is coming together to try to address requests identified from a number of users. This is an informal initiative, but it has a lot of value as the interaction with stakeholders and the gaining of experience on how to address their requirements is. My summary, and I apologize if I didn't go in detail through many other aspects that I wanted to raise. But I think that will give a flavor of this new service-oriented research agenda that I was mentioning at the beginning of my presentation. So I mentioned the fact that there is a broadening range of users for climate information for the next 30 years. They have to make decisions in the near term, and near term ranges from a few weeks into the future to up to 30 years. And they are basically ready to engage very closely with the climate research community and the climate operations to get the best information possible. It's in their own interest to get the best information possible out of the work that we are doing in the physical aspects of climate modeling. There is a clear lack of standards for verification, data dissemination, the definition of observational references, and many other aspects that require the intervention of many different actors, starting from the users and going all the way to modelers. And it's in everyone's interest to address this gap, because otherwise we are going to be requested as climate change becomes more and more important for society. There are still lots of research topics to be explored. There is aspects, as I mentioned before, on how to address the issue of observational uncertainty, how to measure it, how to deal with it in many aspects of what we are currently doing. The questions of model selection, using emerging constraints or model weighting, or many other aspects, many other solutions that could be tested and implemented. The merging of prediction and projection, the model improvements in many different aspects, including model resolution and many more. Documentation and training, as well as the involvement of climate researchers in communication, is fundamental. communication will only be efficient if there are professionals of communication and user engagement who are working together neck to neck with climate researchers and operational actors. And just my final line, all this requires investments, and we have to make clear to the managers of the instruments that we are using that we are ready to work in a transdisciplinary way, but that none of this will happen if we don't improve the observational networks, if we don't increase the collaboration across the different communities, Cortex, CMIP, climate forecasting, to reduce all aspects of model error, and if we don't improve models in a serious way. And I'll leave it there. Thanks very much for your attention.
And thank you, Francisco, for this very interesting talk. I would like to remind our audience, we have more than 100 participants, to post a question on the panel on the right hand. When you click on the questions, you are able to post your question. Just while we are waiting for the first questions, Francisco, I'd like to ask two questions. One is more technical, and it relates to the slide where you spoke about bias adjustment. And I think that was referred to the work by Manzanas. And you mentioned that some bias adjustment methods degrade the forecast quality in many places while gain the forecast quality in some others. Is there any method to judge the quality of the bias adjustment, comparing the places where we lose the quality of forecast compared to the places where we gain it?
Shall I address this one, and then we can go to the second question? Yeah. Yes. So I have to clarify that this metric, the RAAS probability score, is looking at anomalies only. So we shouldn't forget that we should always correct at least the mean of our climate forecasts. This is a fundamental aspect. So what I'm talking here is about the degradation of some aspects of the forecast quality. For instance, what we can see here, the areas in red, they are in red because the correlation between the observations and the forecasts is degraded in the bias adjusted forecasts. While the areas in blue illustrate those areas in which the reliability of the probabilistic forecasts was so low in the forecasts that we needed to bias adjust to really take into account that aspect of the systematic error. What I try to convey here is that first, bias adjustment is absolutely necessary for a wide range of the users, and two, that bias adjustment being necessary and fundamental still comes at a price. So it's not solving everything, and in areas with low skill, it might make more damage than good.
Excellent, thank you very much. And the other question was more conceptual. You mentioned that we have no analytical framework for multimodal ensemble prediction, choice, or evaluation. Do you think, are there any principle of good practice that we need to follow when we look into multimodal ensemble predictions? So what would be your take on the good practice in deciding how many models, which models, or how to perform the assessment?
In our interaction with the users, and we interact with users in domains like wind energy, agriculture, and insurance, we make two recommendations. The first one is look at all the focus systems available, everything, and make a fair comparison of all the focus quality of all of them in a fair way. And second, unless there is a very obvious clear winner, and winner doesn't mean having a correlation of 0.3 when the others have a correlation of 0.25. For us, this is not a winner. unless there is a very obvious and clear winner, use all of them in a multimodal approach. There are different flavors of a multimodal approach, with weighting, without weighting, but try to escape the trap of choosing the best or the apparently best focus system, unless it's obvious that there is no competition with the others.
Excellent, thank you very much. We have a question by Massimiliano Grancheri, and I read the question. Don't you think that communication should be part of your hard scientist duties instead of leaving it to communicators? Mediators and facilitators are important, but the source of information is created and managed by you. By the way, thank you very much for the presentation, says Massimiliano.
I think it's important to make a distinction here between the elements and the group. I don't think all the climate researchers, climate modelers, have to worry about communication. What I think, and that's what I tried to convey from the beginning of the presentation, that what is needed is to identify transdisciplinary groups in which the different competencies are put on the table, and there are ways to make the most of those different competencies and experiences. So while the person working on convection in a global model might not be an expert on communication, maybe that person is requested every now and then to contribute to a fact sheet or to provide some feedback on video, and that would be already enough. The convection modeling expert doesn't need to be an expert on communication. What needs to have is a clear channel to collaborate with communication experts, with user engagement scientists, with practitioners and intermediaries that can really make the right questions to this research profile. And this is something that is already happening in many different places in Europe, and CMCC is a good example of this. So it's not by chance that that you're trying to cluster in the different actors in Italy that have something to say about climate change. And we try to do something similar here at the BSc with our different groups that are working together in a symbiotic way. So, in my opinion, this is really what can make a difference in the future, is working together across many different fields that they all need each other.
Excellent, thank you very much. The next question is from Anna from the Climate and Environment Division of the UN Food and Agriculture Organization, FAO. Francesco, you mentioned the importance of interdisciplinary use of climate data. We are very interested in climate impact assessment in agriculture using downscale climate projection and I guess also prediction. Can you discuss if you have any components of your work focused on the use of climate forecast for agriculture impact assessment?
We work with several actors who have interest in crop yield mainly. With these actors, we try to follow two routes. The first one is to try to illustrate to them what is the impact of the downscaling, for instance, or the bias adjustments. So we have no vested interests in the sense that we don't have to sell anything. We are a sort of auditors of whatever is available there, both in terms of methods and data sources. So the role that we play with the different sectors is to assess the different methods and sources, to try to illustrate to them what are the advantages and inconveniences. And when we do this in the case of agriculture, on one side, we try to find the simplest way for them to use climate data. So for instance, to use climate indicators that they could use with empirical relations between observed crop yields and climate indices. And this is something that we do, for instance, with the JRC in ICREA, or we try to provide them with temperature and precipitation and radiation and wind, so that they can force crop models. And this is something that we do with IRTA. It's a research institute here in Barcelona on agricultural techniques. And we try to, on one side, show them what is the impact of downscaling all these different variables down to the parcel, for instance, spatial scale, which is the one that usually they're interested in. How much do they lose by doing this? What is the actual quality of the climate variables when we do this? And what is the best way of using these climate data? For instance, how to use ensemble forecasts. Try to avoid taking a single member. If they have limited computational resources, helping them on running their models so that they can cope with these different scenarios of climate data. So somehow what we try to do is to walk along with the impact modeler, so that we both learn what are the advantages and inconveniences of using climate data. And I'm talking of not just the climate data that we generate here at the BSc, but all the different sources that are available out there.
Excellent, thank you very much. Then there is a comment by Bernd Egan, which I'm happy to pass to the audience. It's more a comment, not a question. Paco mentioned the evaluation and quality control contract led by BSc. There is a similar contract led by Telespazio Vega, with Met Office contributing on sectoral information services of C3S operational services across the total of 10 sectors. And Met Office is leading on insurance and disaster risk reduction. So if the audience is interested in getting more insight or more information on that contract, please feel free to contact Bernd Egan at Met Office. The other question is from Adrian Perels from FMI, the coordinator of EU MAX project that was looking at the market with climate services. And his question is, would you see, Francisco, would you see possibilities for impact-weighted climate forecast? And he offers also further clarification, saying integrating impact weighting in the ensemble weighting or other correction methods? Question mark.
Absolutely yes. So this is something that has to be explored. I think there was an attempt to do this thing. I was discussing this with Carlo Bontempo a couple of years ago, but I haven't seen much done in that direction. But for sure that they would make good sense, and it's probably the best way to construct a multimodal.
Excellent, thank you very much. And then we have probably last question for which we still have time, is from Jan Dutton. And the question is, are you, Francisco, concerned about competing with similar private sector applications that are already available?
Not necessarily. We work mainly, as I said before, with a lot of public and private actors, but we are not providers of climate information. So we just go to the public sources of data that are available out there, both observations, climate predictions, climate projections, and we work with those actors, both in the public and private domains, to teach them and work with them to show them what are the best practices, to act as auditors that have no specific interest on any specific focus system or simulation, to show them what a fair comparison in terms of focus quality can offer. So somehow we are complementary to what the private sector on the service provision can do. Basically, as a public institution, part of the Spanish government, we cannot do competition to the private sector in that field. So what we try to do is basically what the Commission is asking for, which is to foster the creation of a market of climate services.
Thank you very much, Francisco, and thank you very much, Jason, for your very interesting talks. Thank you to all participants. I have just one information about the next webinar. So if I might get the presenter's role. Okay, thank you. And the forthcoming CMCC webinar will be on oceanic mesoscale in the climate machine, and it will be on June 25th, as usual at 12:30 Central European summertime, and the talk will be given by Dorotea Jovino from CMCC, and the webinar will be moderated by Enrico Scocimaro. There was some question about, whether this webinar was recorded. It was, and it will be uploaded on CMCC YouTube channel. You can read, the connection, but you will be also sent an email, including the PDF version of the presentation of the slides by Jason and Francisco. So if you have any further question about the webinar, please send us an email. If you would like to get in touch with EUCP project team, visit our webpage or send us a simple message. You might subscribe to our newsletter. You might get in touch with us if you are interested in operational use of climate prediction. We are building a large user forum, and you are very welcome to join that forum and work with us on developing well-designed climate prediction systems in your field. Thank you very much again, and have a nice day.